Good evening, all of you. So you people have any doubts regarding that? Yesterday mains paper, Saturday mains paper and today advanced paper, you people can ask me. I'm giving you 5 minutes time for asking the doubts in the exam paper. And if no doubts are there, I will continue myself as usual. So I will be waiting for your doubts. Any? So only one person, it seems, have doubts. It's nice. And yes, Mr. Abhigyan Ravi.
Yes, sir. Sir, in exam I don't have doubts, sir. In material I have doubts, sir. Sir, material, sir. Page number 195. Question 28, sir. 28.
Question 20?
8.
To 8.
Yes, sir.
Electron is continuously accelerated in vacuum tube by applying potential difference if the de Broglie wavelength is decreased by 10%. So decreased de Broglie wavelength is 10%. The change in kinetic energy of the electron is nearly. So directly they are asking lambda 1 by lambda 2. Lambda 1 by lambda 2 is equal to root over Ke2 by Ke1. Directly compare. So lambda 1, and if you are taking that lambda 2 is 0.9 lambda 1 because 10% decreased.
Yes.
Then kinetic energy 2 is how many times of kinetic energy 1? That is they are asking.
Oh, okay, sir.
Next. So any more people? Doubts from today's question paper or Saturday mains paper or material? You can ask any question. I'm giving you 5 minutes time for asking doubts. Just only for interaction if you have any clarities or doubts. Mr. Sushant, please continue.
Sir, in exam only, sir.
Carry on.
Sir, the number of spectral lines observed in emission spectrum of hydrogen when electron falls from 6th orbit to 1st orbit, sir.
So 6 to 1 it is, right?
Yes, sir.
Answer is 10.
Sir.
Directly, what is number of spectral lines formed, man? N2 minus N1 into N2 minus N1 plus 1 by 2. Directly apply that. N2 minus N1 is 5. So 5 into 5 plus 1. Sorry, 5 into 5 plus 1 by 2. 15 it is.
Sir, but it's given as wrong, sir.
Okay. So in the question, did they mention hydrogen or hydrogen single atom?
Hydrogen only, sir. That's it, hydrogen.
They didn't mention atom, right?
No, sir.
Then 15 is the answer.
Sir.
And did they mention anything without emitting line in Lyman series or Balmer series likewise conditions?
No, sir. No connections.
Then answer will be 15.
Okay, sir. It's given as wrong, sir, in key.
Yeah, it will be changed then.
Okay, sir.
Next.
What is the number of lines in visible spectrum of hydrogen when the electron is in 5th excited state?
5th excited state means 6th orbit only.
Yes, sir.
6th orbit to 2nd orbit. How many lines are possible? sixth orbit to second orbit. How many lines are possible? Draw them.
10, sir.
No, that is wrong. Only second orbit, not all. Only they are asking visible line, right?
Yes, sir.
So 6 to 2 possible, 5 to 2 possible, 4 to 2 possible, 3 to 2 possible, only 4 are possible.
Okay, sir. I didn't
Understood?
understood now, sir.
Right. Any more?
Sir, one more doubt, sir.
Carry on.
Compton effect can be explained by Maxwell electromagnetic theory. Is it correct, sir?
Compton effect is explained by Maxwell's
Electromagnetic theory.
electromagnetic wave theory. Not sure. What are the remaining options?
The energy associated with an atom is always negative.
Energy associated with electron or atom?
Electron, sir. Correct. That option is correct.
Okay.
Multi-correct, sir.
Okay.
Energy difference between successive levels in hydrogen atom decreases with increase in N value.
Yes, it is.
Emission spectrum of sodium vapor contains two dark lines on bright photographic plate at 5890 angstrom and 5896 angstrom.
So that is D1, D2 lines over sodium spectrum. Emission spectrum or absorption they gave?
Emission, sir.
Emission means bright lines over dark background.
Yes, sir.
Bright lines. Two bright yellow lines over dark background.
Sir, they gave some wavelength, sir.
Yeah, that's okay. The two wavelengths should be very close.
Understood, sir. Only three are correct.
Yes. Medhan, stop, Mr. Carry on.
Sir, yes, sir. Srihit asked no, sir, just now one question.
Yes.
That question, sir, I have marked all the means correct answers which you said, sir. But still, it is given wrong, sir, for me.
So they gave only 3 correct answers.
Means I don't know the correct option, sir. But means the 3 sentences which you said, I have marked those only, sir. But they gave it is wrong.
Okay, so let me see the paper then. Until that, I cannot give guarantee. So what you people are saying that I cannot believe that theory-based questions. If it is numerical, I will give you answer directly. But the theory-based, until I see the statement, I cannot say.
Okay, sir. Thank you, sir.
Right. So any more? Any more questions you people have? If anything is there to ask, please carry on. I will be waiting for your questions. Okay, it seems that no people have doubts. So shall I start? Yes or no? Medhan, stop.
Sir, in exam, sir, 2 questions were repeated, sir.
Okay.
24 and 26, I think for everyone it is, sir.
Okay.
And for the 26th, the question is, sir, if lambda naught and lambda be threshold wavelength and wavelength of incident light, the velocity of the photon ejected will be, sir.
Velocity of photon ejected or photoelectron ejected?
Sorry, sir, photoelectron ejected will be, sir.
Okay.
Answer is square root 2 hc by m into lambda naught minus lambda by lambda naught into lambda, sir.
But already we gave the classroom derivation, right?
Yes, sir. But that is correct for 26th, sir. But in 24th, sir, same question is repeated, sir, in exam.
Okay.
So, sir, that time it was given wrong, sir. Now, when we check, the question has only changed completely, sir.
So question is changed.
Yes, sir.
Okay.
It is not tallying with 20 means the exam question and no question, sir.
Okay, okay. That I don't know. Then After seeing the PDF file, then I can give you clarity over that, whether the two questions are printed same or different.
Okay,
Okay.
sir. Thank you, sir.
So right then, now let us go for the next topic, that is shapes of atomic orbitals. Shapes of atomic orbitals. So what are the shapes of various orbitals and what is the probability picture? We know that what is meaning of orbital? Well, orbital is a three-dimensional space around the nucleus. Three-dimensional space around the nucleus where the probability of finding electron is more than 95%. Probability of finding electron is more than 95%. That is what we call orbital. And let us go for the first one. We are going for s orbitals. S orbitals. Okay, say a shape of s orbitals I am giving. So s orbitals are said to be spherically symmetrical around the three coordinate axis. Spherically symmetrical around three coordinate axis, and also said to be non-directional. Non-directional stands for the probability of finding electron is not along a particular axis. The probability of finding electron is not along a particular axis. So it will be equidistant in the three-dimensional space, equidistant from the nucleus in the three-dimensional space, whether it is x-axis or whether it is y-axis or whether it is z-axis, and whatever the imaginary reference axis you are taking. So the probable region is assumed to be spherically symmetrical. And for imagination, you just imagine a lemon. Just imagine a lemon and assume that the lemon is hollow. And assume that around lemon, imagine a cricket ball. So cricket ball, if you take exactly, if you put the lemon inside the cricket ball, having the common center, exactly. Imagine the common center, and around that we have a lemon, and we have the cricket ball, and around that football. If you just imagine the three spherical structures. One is lemon, other one is a cricket ball, and other one is, if you take that as football or volleyball. All three are having the common center. Assume that the lemon is hollow. Right? So if you cut the cross section, if you just cut them exactly into half, so what is the projection they look like? That we need to understand. Okay. Right. So for imagination, I'm giving the three-dimensional pictures. So just follow them carefully. And as I'm taking three coordinate axis first, I'm taking. So assume this is the 3-coordinate axis. This is the 3-coordinate axis. Assume that. So I am taking this as x-axis and y-axis and z-axis. Listen up carefully. So around the nucleus, at nucleus, we know probability of finding electron is 0. We know probability of finding electron is 0. And when you are taking the cross-sectional view, only cross-sectional view, so probability of finding electron is spherically symmetrical. This is the appearance you will have around the nucleus, appearance of probability. So as we say that electron cannot be traced out exactly at well-defined position, cannot be traced out at well-defined position. Instead of that, we are giving some region where electron can be identified. And in that electron probability region, if you draw the outer lines, contour surface, what we call contour surface or boundary surface. So what does a boundary looks like? The boundary just looks like a sphere, three-dimensional sphere. And this is picturization for 1s. 1s. Okay. Now, around the 1s orbital, there will be one more electron probable region. There will be one more electron probable region I am taking. So just imagine that. So between 1s and 2s, you have no chance of finding electron. So electron can be identified either in 1s or in 2s. So in between the gap, the probability of finding electron is perfectly 0. Because as we know, electron energy levels are quantized. So it may be in the first orbit or it may be in the second orbit. Means that electron can be picturized and can be identified either in the first spherical region around the nucleus or second spherical region around the nucleus. Okay, so this is probability picture we are giving, not exactly well-defined circle we are drawing. We are not drawing well-defined circle. We are giving the region so in which electron can be identified. And this is 2s. And if you are going for 3s, so this is probability picture for 3s. Just imagine. So this is the total cross-sectional view. Total cross-sectional view of the respective diagrams I am giving. So along the 3-coordinate axis, you can consider them, all were assuming that perfectly spherical in nature. Perfectly spherical. Okay, na? So between electron can be identified either in 1s or in 2s or in 3s. So it is very clear. So all s orbitals are spherically symmetrical. If you draw the outside surface diagrams, so that is indicating clearly this is 1s, this is 2s, and this is 3s. That's what I told you. Just imagine a lemon and around that cricket ball and around that football. Having some thickness, not a well-defined layer, having some thickness. So in the thickness, in the region, we can find electron. So that is probability pictures for 1s, 2s, and 3s, and all were three-dimensionally present. So that is 1s, 2s, and 3s picturization. And clearly I'm saying that electron cannot be present in the gap of 2s and 3s. So this is the three-dimensional region three-dimensional space, spherical space, where probability of finding electron is 0. So this space is called radial node. We call this as radial node. So draw this diagram. Right? So radial node is a three-dimensional space. Three-dimensional space, I am giving that radial node, or which we call as a spatial node, or which we call as a spherical node names. Spherical node. So what it means exactly? A three-dimensional space. Three-dimensional space in which probability of finding electron is 0. Probability of finding electron is 0. That is what we call radial node. Three-dimensional space is radial. Two-dimensional plane, it is angular. If it is two-dimensional, we call as angular. If it is three-dimensional, we call as a radial, spatial, or spherical. So between 2s and 3s, there is a radial node. And between 1s and 2s also, there is radial node. Between 1s and 2s also, there is radial node. You cannot find electron in between the gap of 1s and 2s. So this is just a simple probability picture for s orbitals. Probability picture for s orbitals. Yes, Mr. Anish.
Sir, means you told probability of finding electron is 0, no, sir, in radial node.
Yes, it is.
Sir, so electron cannot pass through that space?
Electron can pass through, but you cannot find. Electron is not staying there.
Okay, okay, sir.
Electron can be excited and can be de-excited. Well, that is not the question here. Okay. So this is radial node concept for only spherical or spatial or radial. That's why I told it is non-directional, because along x-axis or along y-axis or along z-axis, it is equidistant. Probability region is equidistant, so it is non-directional. And I am giving that formula for number of radial nodes. Number of radial nodes for any orbitals will be given by n minus L minus 1. Number of radial nodes formula we write as n minus L minus 1. Number of radial nodes formula. And example if you write. So example, so number of radial nodes for 5s is, what do we write now? N value 5, L value 0 for s orbital, that is 5 minus 0 minus 1, so 4. Means that, meaning is between 1s 2s there is 1, 2s and 3s there is one more, 3s and 4s there will be one more, 4s and 5s there will be one more. Total 4 regions are there where you can find radial nodes. And one more point I'm saying, that at node, whether it is radial or angular, psi square will be 0. That is compulsory. At node means probability 0. Psi square indicates what? Probability density of electron. So probability density of electron will automatically be 0 at node. You cannot find electrons at all there. At node, whether it is radial or angular, irrespective, psi square should be 0. So number of radial nodes for 5s is given 5 minus 0 minus 1, that is 4. And for any ns, number of radial nodes for ns orbital is directly n minus 1. Directly n minus 1. Number of radial nodes for ns will be directly n minus 1 because L value is 0. So this is the shape of respective s orbitals. Shape of respective s orbitals. And just what it looked like, I'm giving you the small picture representing 1s, 2s and 3s representation, how it looked like, just for visualization. Just for visualization I'm giving. So this is representation for 1s, the cross-sectional view I'm giving. 1s. So representation of r theta pi and s orbital picture I'm giving here. So that is representation for s orbitals. And if it is clear, then we can move on to p orbitals. We are going to p orbitals then. Next, let us go for the shapes of p orbitals. Shapes of p orbitals. So p orbitals are dumbbell shape, and also said to be directional. They are directional. So dumbbell shape and directional. Dumbbell shape and directional. So what is exactly meaning of these shapes of p orbitals? Let us see once. So there are three kinds of p orbitals, commonly pxy, py, and pz. Px, py, and pz are the orbitals we have. And let's visualize the px orbital first. Px orbital first. So I am taking every time the three coordinate axis. Every time I am taking the three coordinate axis, and you people try to draw remaining to one. I will explain, and remaining you need to draw them. Okay, so I am taking that. So this is so three orbitals I am taking. Let us go for px orbital. Px stands for probability of finding electrons. Probability of finding electrons is along x-axis, x, y, and z. So if you are taking the probability picture, so this is a probability picture of s or px orbital. I'm giving that. See once, as it is not, the color is not enough. So I'm taking that here. So this is the representation of px orbital. Probability of finding electron is along the positive x as well as negative x in the form of dumbbell shape. For weightlifting dumbbells, you know, for doing the physical exercises, what the dumbbells we use. So that is the shape we write, dumbbell shape. And see carefully, in so many books they will be mentioning that, in so many books they will mention that if you are taking x-axis, the representation of the x will give like this. But keep in mind, it doesn't mean electron is traveling in the path. Electron, if it is traveling in the path, it should pass through nucleus. That is not possible. Electron never travel through nucleus. And this diagram means, the diagram meaning, I am saying that the diagram meaning is, it is just electron boundary diagram. It is, means that the probability picture outline, if you draw the outline, what it appears to be, dumbbells. So two dumbbells, two lobes, what we call technically. Two lobes are there along, one is positive x and other one is along the negative x. So this is representation of px, and you know px starts from second shell. Px starts from the second shell. Now I am giving this is 2px, and if you are trying to visualize 3px, so listen up carefully. I am taking the visualization of 3px. The visualization of 3px. So between 2px and 3px, there will be again a spatial node, because you cannot find electron in between the gap. You cannot find electron in between the gap. So clearly, we can say that the probability picture, the outer one, is what we call as 3px. The outer one is what we call as 3px. So clearly, I represented here, right? So this is 3px and this is 2px, and between that we have a space, that is what we call radial node again. Radial node again. Keep in mind that radial node again. So 2px and 3px, represent them clearly. Between 2px, one lobe, just imagine the folding of your hand representing one lobe, and around that, if you just imagine one more bigger hand, between that hand and this hand there is a gap, three-dimensional gap again, the spherical gap called one radial node. Because for px, what is number of radial nodes? Number of radial nodes for 3p, if you want to write 3px, n value, L value, we know n value 3, L value 1 minus 1, that is 1. So it is only one radial node for 3px, but for 2px, no radial nodes. For 2px, there is no radial nodes. Okay. Now, this is about radial node part. Okay. Now, clearly, listen this. If you are taking that px orbital, this is px orbital along positive x and negative x we have, and this is y axis and this is z axis if you imagine. Z axis if you imagine. So y axis here, z axis here, this is z axis and this is y axis. So where is yz plane identified? Where is yz plane identified? For 2px or for px orbital, whether it is 2px or 3px, point is same. For px orbital, yz plane, if you imagine, yz plane has no electrons. Yz plane has no electrons. So it is a planar node. Planar node, nodal plane, we can say that. Nodal plane, we can say that. Or angular node, we can say that. Angular node, we can say that. So for px orbital, probability is only along x-axis, positive x and negative x. So in this plane, if you take exactly here, there is no way of finding any electron over that, no electrons over that. So that for px orbital, yz plane is called nodal plane. Yz plane is called nodal plane. So for px orbital, yz plane is nodal plane. Two-dimensional is called nodal plane. Three-dimensional is called spatial. Similarly, for py orbital, xz plane is nodal plane. For pz orbital, xy plane is nodal plane. We can say that. So these are the nodal planes for px, py, and pz orbital for every orbital how many nodal planes are there here? So from this, therefore, number of angular nodes, we can directly give the formula. Nodes or nodal planes. Nodal planes will be directly L. So how much is mean? What is the L value for P sub shell? So L value for P sub shell is 1. So directly there will be only one angular node. One angular node. There will be one angular node. So number of radial nodes formula n minus L minus 1, and number of angular nodes formula is L. Px orbital, there will be only one nodal plane. Next. So if you are taking that, the above diagram, if you want to picturize Py. So I am taking this as y-axis. So first I am representing that 2Py. 2Py. The boundary surface, if you just picturize, the boundary surface, if you just picturize, that is the outline we can represent normally. Normal way of representing that. So this is along Py. So this is 2Py. And similarly, if you want to represent 3Py, so just see this one. So this is probability picture of 3Py. So 2P and 3P, again, there will be a spatial node. There will be a spherical node. There will be a spherical node. So that is representation of 2Py and 3Py. And you only try to represent for 2Pz and 3Pz. For Py, which is nodal plane, x, z plane, x is here and z is here. So this horizontal plane, exactly, if you are taking that, has no electron in that, and directly we can say them. So Px, Py, and Pz representations. Px, Py, and Pz representations. So Px is along x-axis, Py is along y-axis, Pz is along z-axis. Represent them clearly. So number of angular nodes will be given by directly L, and number of radial nodes will be given by directly n minus L minus 1. And total nodes, if they ask, sum of both. Total number of nodes, if they ask, sum of both. Total number of nodes will be equal to sum of what? Radial nodes plus angular nodes. And radial nodes formula n minus L minus 1 plus angular nodes L. So directly what we write, n minus 1. So total number of nodes will always be equal to n minus 1. Total number of nodes will always be equal to n minus 1. So I hope it is copied, yes or no? There are pictures of Px, Py, and Pz. It's copied, yes or no? Right. Okay, right. So this is a simple idea of shapes of various p orbitals and number of nodes, radial nodes. Radial nodes always depends on n principal quantum number. You need to think about the principal quantum number for it. Whereas the angular nodes depends only on the particular orbital orientation, particular orbital, the electron regions. So this is the simple outline representation of respect to p orbitals 3. So px along x-axis, py along y-axis, pz along z-axis. So 3 coordinate axis representation. Okay, suppose if you imagine for pz, this is x-axis and this is y-axis. Where is xy plane? So this is xy plane completely here, right? So over the xy plane, no electrons are found. As no electrons are found, so what we can say, xy is nodal plane. Nodal, whenever you are using the word, you cannot have chance to find electrons. There is no way of finding electrons in that. There is no way of finding electrons in that. So p orbitals are directional. Undoubtedly, p orbitals are directional. Next. Is it over? So if you know orbitals, then we can give you that orbital wave functions, psi graphs, psi square graphs, 4 pi r square psi square dr graphs. That is the next part we need to go through. Next, I'm going for d orbitals. So shapes of d orbitals I'm going for. And before that, I would like to show you a small video presentation so that it will be easy to you for understanding. 1 second. So once watch it. So it's just only explanation about the orbitals. See carefully. So that is s orbital representation. That is three orbitals of p together. Three orbitals of p together. Px, py, and pz. So for individual understanding, I give separate representation for px, py, and pz. But the three are not separable. They were all alike. Keep in mind that do not try your imagination to keep all the orbitals at a single point and try to visualize them. It's somewhat difficult. So three-dimensional visualization is more important rather than drawing them on paper. See carefully, in d orbitals, there are two categories of d orbitals. Two categories of d orbitals we have. So one is along the axis orbitals and other one is in between axis orbitals we call. First visualize and then we will discuss. Just to see them, what it is. So first one is given here as dxz. First one is given here as dxz. Okay. So I have no technique to write on the screen over the video. Just we have to watch it. Orbitals. That is dxy. See, identify that it is in between x-axis and y-axis. You know perfectly that Q1, Q2, Q3, Q4, four quadrants of XY plane. So they were lying exactly in between them and having the double dumbbell shape. Double dumbbell shape. So this is called dx square minus y square. This, the lobes are along x and along y. Along x and along y. Z-axis is completely free. Now electrons are there along z-axis, and do not say that z-axis is a nodal plane and there is no nodal axis. There is no nodal axis. At least it should be a two-dimensional plane or three-dimensional space, but not a single line. But not a single line. all orbitals together, if you want to visualize, that is a picture. That will be very difficult to imagine. That will be very difficult to imagine, okay? Next one. I'm going to give you that one more. Once see that. So that is representing s orbital. That is representing s orbital. So that is representation of 1s, 2s, and 2p. Visualization of 1s, 2s, and 2p. Right? So next one more I am giving you for visualization of these orbitals. So once see this also to get clear idea.
We learn about shapes of atomic orbitals. The orbital wave function or psi of an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave function as a function of r, which is the radius or the distance from the nucleus, are different. According to the German physicist Max Born, the square of the wave function, which is the psi square at a point, gives the probability density of the electron at that point. The variation of psi square as a function of r for 1s and 2s orbitals is shown here. Notice that the curves for 1s and 2s orbitals are different. It may be noted that for 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces, or simply nodes. In general, it has been found that ns orbital has n-1 nodes. That is, the number of nodes increases with increase of principal quantum number n. In other words, the number of nodes for 2s orbital is 1, 2 for 3s orbital, and so on. These probability density variations can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in a region represents electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals gives a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in space for an orbital on which the value of the probability density psi square is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say around 90%. One may ask, why do we not draw a boundary surface diagram which bounds a region in which the probability of finding the electron is, say, 100%? The answer to this question is that the probability density psi square has always some value, howsoever small it may be, at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for a s orbital is actually a sphere centered on the nucleus. In 2 dimension, this sphere looks like a circle. It encloses a region in which the probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the s orbitals are spherically symmetric. That is, the probability of finding the electron at a given distance is equal in all the directions. It is also observed that the size of the s orbital increases with increase in n. That is, the size of the 4s orbital is greater than that of 3s orbital, which is greater than that of 2s orbital, which is greater than that of 1s orbital. And the electron is located further away from the nucleus as the principal quantum number increases. In our next video, shapes of...
So the next I will show you one more, and that is the story for the p orbitals, how they look like.
We will learn about shapes of atomic orbitals. The orbital wave function or psi of an electron in an atom has no physical meaning. It is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of corresponding wave function as a function of r, which is the radius or the distance from the nucleus, are different. According to the German physicist Max Born, the square of the wave function, which is the psi square at a point, gives the probability density of the electron at that point. The variation of psi square as a function of r for 1s and 2s orbitals is shown here. Notice that the curves for 1s and 2s orbitals are different. It may be noted that for 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from it. On the other hand, for 2s orbital, the probability density first decreases sharply to 0 and again starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. The region where this probability density function reduces to 0 is called nodal surfaces or simply nodes. In general, it has been found that ns orbital has n-1 nodes. That is, the number of nodes increases with increase of principal quantum number n. In other words, the number of nodes for 2s orbital is 1, 2 for 3s orbital, and so on. These probability density variations can be visualized in terms of charge cloud diagrams. In these diagrams, the density of the dots in a region represents electron probability density in that region. Boundary surface diagrams of constant probability density for different orbitals gives a fairly good representation of the shapes of the orbitals. In this representation, a boundary surface or contour surface is drawn in space for an orbital on which the value of the probability density psi square is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability density is taken to be good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is very high, say around 90%. One may ask, why do we not draw a boundary surface diagram which bounds a region in which the probability of finding the electron is, say, 100%? The answer to this question is that the probability density psi square has always some value, howsoever small it may be, at any finite distance from the nucleus. It is therefore not possible to draw a boundary surface diagram of a rigid size in which the probability of finding the electron is 100%. Boundary surface diagram for a s orbital is actually a sphere centered on the nucleus. In 2 dimension, this sphere looks like a circle. It encloses a region in which the probability of finding the electron is about 90%. Thus, we see that 1s and 2s orbitals are spherical in shape. In reality, all the s orbitals are spherically symmetric. That is, the probability of finding the electron at a given distance is
This is already over and we have to cover. So this one already covered there? Not yet.
video, we will learn in detail about the shapes of orbitals. In our previous video, we had studied in detail the shape of 1s and 2s orbitals. In these diagrams, the nucleus is at the origin. Here, unlike s orbitals, the boundary surface diagrams are not spherical. Instead, each p orbital consists of 2 sections called lobes that are on either side of the plane that passes through the nucleus. The probability density function is 0 on the plane where the 2 lobes touch each other. The size, shape and energy of the 3p orbitals are identical. They differ, however, in the way the lobes are oriented. Since the lobes may be considered to lie along the x, y or z axis, they are given the designations 2px, 2py and 2pz. It should be understood, however, that there is no simple relation between the values of ml and x, y and z directions. Because there are 3 possible values of ml, there are, therefore, 3p orbitals whose axes are mutually perpendicular. Like s orbitals, p orbitals increase in size and energy with increase in the principal quantum number, and hence the order of the energy and size of various p orbitals is 4p is greater than 3p, which is greater than 2p. Further, like s orbitals, the probability density functions for p orbital also pass through the value 0. Besides, at 0 and infinite distance, as the distance from the nucleus increases, the number of nodes are given by n-2. That is, the number of radial node is 1 for 3p orbitals.
That story is enough for us, and I hope you got a better picture over the orbitals. And now I am going back to the where we stopped there. So p orbitals over, and let us go for d orbitals. So go for the shapes of d orbitals. Shapes of d orbitals. So we know that there are 2 kinds of d orbitals, as I told. 2 kinds of d orbitals we have, as I already told you. One is the 3 orbitals we can say along the axis, and 2 orbitals we can say are in between the axis. So we have two kinds of orbitals, dxy, dyz, dzx, and dx square minus y square and dz square. These three are in between axis orbitals. We can call them in between axis orbitals. And these two are called along axis orbitals. Along axis orbitals. Okay. And if you see that first one, I will explain dxy, and the remaining three are, remaining two are similar. So dxy I'm going for. Dxy I'm going for. So for easy imagination, I am taking three coordinate, just only two coordinate axes I am taking now for easy imagination. So let us take, this is x-axis, this is y-axis. So probability of finding electron in dxy orbital will be only in between whatever we write that. So it is always in between q1, q2, q3, q4 we can express. So this is probability picture we can express here. So in q1 we have probability region, and in q2 we have another probability region, and in q3 we have another region, and in q4 another region we have. So this is the probability picture for dxy and its overall appearance, whatever we write that here. So this is representation of dxy. So this is x-axis, this is y-axis we represent. X-axis and y-axis we represent. Okay, so for dxy orbital, I'm writing here for dxy orbital. So what is the number of radial, no, I mean, what is number of nodal planes? We write L value. For D, L value is 2. For D, L value is 2. So undoubtedly what we say that then, so for dxy orbital, yz and xz are nodal planes. Similarly, for dyz orbital, xy and xz are nodal planes. And for dxz orbital, similarly we can write xy and yz are nodal planes. This is way of writing them. Way of writing the nodal planes for dxy, dyz, and dzx are similar. They are similar. Next, we need to go for the remaining two orbitals, what they are. Dx square minus y square and dz square we have. Dx square minus y square and dz square we have. Okay, and next I'm going for dx square minus y square. So I am going for dx square minus y square and dz square. Directly I am showing the orbitals pictures then. I'm directly showing the orbitals pictures then. See once what they look like. So these are the orbitals picture. These are the orbitals picture for dz square, for dz square, dx square minus y square, and dxy. Okay, and the remaining two, how they appear to be. Remaining two also I'm giving for visualization. Visualization I'm giving. So for any d orbital, the total nodal planes will be 2. Total nodal planes will be 2. So these are the shapes of various orbitals of d. For dz square, which is having a special shape, which is having entirely special shape. Okay. Next. Next, F orbitals also I'm giving only for pictures, means what they are identify enough. What are the names of respective F orbitals, and no one will ask you that questions over what is the shape, because F orbitals are complicated shape and complex shape we can call. D orbitals are double dumbbell, but F orbitals are having complex shapes. F orbitals are having complex shapes. So these are the shapes of various F orbitals. So F orbitals are F z cube, F x y z, F z of x square minus y square, F x of y square minus z square, F x cube, F y cube, F y of x square minus z square minus x square. So these are the orbitals of F we have. Only the names enough. You no need to remember the pictures. You no need to remember any pictures here. Okay, these are the shapes of F orbitals. So shapes of various F orbitals: F x cube, F y cube, F z cube, F x y z, F x of y square minus z square, z of x square minus y square, y of z square minus x square.